Starting. Okay, so I wanted to say a couple words, maybe more than a couple words about the TNB basis uh, because it's important. So one thing to point out is that we haven't even started doing calculus yet, although all of these things are inherently uh, unnecessary for describing rates of change. The geometry that we've been developing over the last few weeks, the last two chapters, is important for basically describing things in an efficient way. So what we've seen is, I mean, this is kind of calculus, but really the motivation here is that we're talking about uh, sort of getting at the geometry in terms of the directions in which things are changing. So before we get to the TNB basis, I want to start by sketching a curve here just to represent our function r of t, to point out one thing that sometimes I see in the homework and things like that isn't entirely clear. So this guy gives you a vector. I'm going to call it okay, so let's suppose that this curve is described by r of t, and this point corresponds to r of t0. And somewhere in this coordinate system there is the origin 0. I want to point out that if this guy gives you a vector a, b, c, just to point out that what you're actually being given here is the position vector that corresponds to that point. So what this vector ABC actually represents is this vector. This is the vector ABC, and this is the associated point P ABC on the curve. So all I'm pointing out is that this is going to be important for actually finding or interpreting what the derivative is, because we know that if we wanted r prime of t, for example, we would have to compute the limit as delta t goes to 0 of the vector r of t plus delta t minus r of t divided by delta t. So that's the definition of the derivative in this case. So really what we're doing is, if I erase some of this stuff and just get the sort of key points out here. So if I call this r of t, this vector, and I move this guy a little bit farther, maybe open it up, and this is the vector associated with r of t plus delta t, then I know that by computing r of t minus r of t plus delta t minus r of t, what I'm actually doing is computing this vector right here. So if I outline that in green, this vector is in the direction r of t plus delta t minus r of t. And then so what we would need to do is then adjust that based on the time elapsed to get the appropriate length, that is, to get the actual rate of change, not just the direction of that change. Okay, so this is the basic idea, and what we get from that, of course, is at some point the vector r prime of t is going to be something akin to the tangent line from calculus 1, except now it's a direction that indicates the rate of change of the function describing this curve at each point. Okay, and the problem is that this guy is not necessarily equal to 1. Is not necessarily equal to 1. Necessarily. So what we usually want to do is assume that things are going at unit speed. So as long as we're not at some point t where the length of this vector is equal to 0, we can define a tangent vector t at that point. It's dependent on the choice of time. So I'm using the word point and time interchangeably now, that I can, if I'm at this point, I can think of there being a time that it's at that point, or I can think of it as the point on the curve. So I'm being sloppy with my language here, but this is the way we talk about things generally, a point or a point in time. So if I take the derivative vector and divide it by its own length, what I get is this vector t that points in the same direction as the derivative vector but has unit length. And this is the big difference between t and r. So this is something important to point out. T versus r prime is that they point in the same direction as long as r prime actually points somewhere. If r prime of 0, r prime of t is not the 0 vector, then t and r prime of t point in the same direction. But possibly different lengths. Okay, and so the idea here is that t, it is always unit length. R prime is not. So t is always unit length. Okay, and similarly, if you notice that going through the process about computing n and b, you have the same thing, that once you have your tangent vector t, and you were to look at the sort of rate of change of that vector, so you had some vector t there, at some later point you have a different vector t. If you subtract the difference between those vectors, right, so t would have gone something like this. If I just translate this guy over there, this is my t of t plus delta t. What we get is a vector n that points in this direction. But that is actually not quite right. This would be the vector t prime. It is not necessarily unit length. You can imagine that if you, and so here's the difference. If I look at this, t is changing very slowly. There's not much of a difference between, I'm going to call this t of t, and this guy t of t plus delta t. The difference between these two is very small, so in this case we would get a short tangent vector derivative, whereas if I had something that curved a lot, like that, and my tangent vector was pointing in this direction at some point, and then at some later point my tangent vector was pointing in this direction, so t of t, this is t of t plus delta t, then I know in this case my tangent vector is going to be very, very big. My derivative tangent vector, t prime, would look something like this. So we of course want this vector to be unit length as well. So we define the vector n to be pointing in this same direction but always have unit length. And the way we do that is we define the unit normal vector to be the tangent vector at the time t, its derivative, divided by the length of t. So we normalize it. Okay, so these two vectors are the most important. The binormal vector is also very important. So let me just say what this guy is. So this vector n, and I'm always putting a hat over these to indicate that they're unit length. That's all that hat means, versus the bar. And of course, the book doesn't do any of this because they have boldface fonts. So this is normal. So is the unit normal vector. And it has the following properties. N is perpendicular to the tangent vector, of course. N points in the direction that t is pulled toward as t increases. So what do I mean by that? So if I am moving along my curve from left to right, I'm going to suppose that t goes left to right on this curve. And I have a tangent vector. I'm going to draw this guy here. I'm going to draw this curve differently so that it has a more appropriate orientation given the space that I have. So if I compute the tangent vector at some point, and I compute the tangent vector at some other point, so this is t of t plus delta t, of course, and I align these guys and I compute my derivative geometrically. So I compute t prime of t is going to be in the same direction. So I'm ignoring the length because I'm not going to divide by delta t. So t of t plus delta t minus t of t. What happens when I add those together, or when I subtract those together? Remember how I add or subtract vectors? I move them so that their tails are at the same point. Or I think about taking this guy t of t and then subtracting off the negative t of t. And I'm going to get this vector right there. So we can think about it this way, that when I'm at t, the vector is pointing downward. What kind of a force or what kind of a vector do I need to add to that to get that vector to be rotating so that its angle is changing, to get the vector t of t plus delta t as I move a little bit farther down the curve? And that is that the change that I would have to supply to t of t in order to get t of t plus delta t is this vector that goes upward. And of course, this guy doesn't have the right length because this term didn't get divided by delta t. But of course, when I'm talking about this parallel idea, that's all I care about. So this is just saying, yeah, this vector that I have drawn here in pink is the numerator of my derivative before I take the limit, the difference in tangent vectors between those 2 points. And then so all that n is a rescaled version of that going in the same direction so that it has length 1. So that's the idea of it being pulled toward, that it's pointing in the direction that the tangent vectors are changing. So the tangent vector starts out and going downward, it is then going upward. The necessary change is going to have to be an upward vector. Okay, from those two, if I have then a curve and I'm at some point where I have r of t, remember r of t is actually this vector. to get to the point on the curve. I'm going to call this curve C. Okay, so what I get is I get a tangent vector that I can get from r prime by dividing r prime by its length. I also get a normal vector. So in this case, which way is the normal vector going to go? Just by looking at it. I have to make this guy a little bit darker so it shows up, sorry. So the question then is, without doing any work, can I discern which direction the normal vector is going to be? And in fact, you can use the geometry of this curve in order to figure it out. So the idea is to go something like this. There's a circle that this curve is following, and the normal vector always points toward the center of the circle. So I know that if I were to compute the normal vector using actual coordinates and calculus, I'm going to get this vector, n, and I get that by looking at the rate of change of the tangent vectors. Okay, so now I have two vectors. I can define a third vector. And that is, I can define a third vector, v, given by the cross product of t and n. And this guy is already a unit normal because it's the cross product of two normal vectors. Okay, so it's already a unit vector. Sorry, unit vector, not unit normal. Okay, so which way does it go? If I'm rotating from t toward n in this picture, I know that this vector is going to have to be into the plane. Okay, so that's the geometric setup of these guys. So what happens here is that if I have some curve, then at each point, t, I'm really getting a small t n, and I'm going to have this guy pointing this way out of the page. I get a little right-hand coordinate system for each point in there. So that's the TNB basis at time t, t naught maybe. If this is the point r of t naught. And then as I have elapsed a little bit farther down the line, and I get to here, maybe this is r of t1, then I'm going to have a slightly different setup. I'm going to get a slightly different basis where the tangent vector is still pointing in this direction, t of t1, but now the normal vector is going to be pointing downward. And because of that, my binormal vector is going to be pointing, is going to have a component that points backward into the page. Okay, so the idea is this, that we can think about this instead of all of these things being in regard to our I, J, K coordinate system, I can imagine that there's a little set of coordinates moving along the curve. And that helps with a lot of things in science and modeling and things like that, because sometimes you don't want to, think about a particle moving through some complicated path. Sometimes it's easier to simply have a time-dependent coordinate system where the particle that you're following along this path is at each point at the origin. So applications of this are exactly the kind of chain of coordinates that you use to get the apparent, centrifugal force from centripetal acceleration. that something that actually is a force pointing in one direction appears as a force in the opposite direction when you assume that you're traveling along a straight line instead of in a circle. Okay, so I wanted to do a couple examples of these, but I wanted to talk about the other geometries, or the other geometrical effects here. And so I'm going to draw another curve here. Again, I'm doodling, and I realize that sometimes this geometry is not helpful for those of you guys who like to simply crunch numbers and work through things symbolically. I am completely sympathetic to that, because that's what my learning style was like for a long time. Okay, so I wanted to talk about the planes here. So if we have the tangent vector at some point, there is a plane for which that tangent is the normal vector too. Okay, so this plane, red plane here, this is called the normal plane. So the normal plane at each point, so I'm going to call this at point r of t0, if this is the point r of t0 in the plane. The normal plane has the tangent perpendicular to it. It is one of the two main planes that we get. And so what's special about the normal plane is that both the normal vector and the binormal vector, so in this case, the binormal vector is going to point this way. The vectors b and n lie in the normal plane. So we saw when we were in chapter 2, or chapter 12 rather, if we wanted to find the equation for this plane and we knew two vectors that were in it, b and n, we could compute their cross product and find a third vector that was perpendicular to the plane containing b and n, and that would just simply be our t vector. I'm going to shorten this line a little bit. So this is called the normal plane. So when you think normal plane, what you should think of is thinking about t as like a needle, and this plane as being like a sheet of paper or something like that, where the needle is poking through it with the tangent vector in it. Okay, there is another plane called the osculating plane, and the way we think about the osculating plane is to have the curve C given by r of t, and if we're at some point r of t naught, there is a binormal vector, if I think of the binormal vector as being the main one. So first, let's think about, based on the way this curve is shaped, which way are the t and n vectors going to go? So I'm going to draw them out. Of course, t is going to go this way. The normal vector is going to point downward. And based on my right-hand rule then, I'm going to have the binormal vector pointing into the page. Okay, so there is a plane defined here, and that is this plane, the plane that I'm drawing this on. So notice that B pointing into the planes mean that B is perpendicular to the page. It doesn't have a component that points along the page. It goes straight in or straight out. So when I say page, I really mean the computer screen that I'm drawing things on. And so what happens is that we call this blue curve the osculating plane, or this green plane. The osculating plane. Of course, that happens at some point r of t0. And it has the properties, oscillating plane has b perpendicular to it. And what we know here is that the vectors t and n lie in this plane. Okay, so important to notice here also is that I can use my right-hand rule. Because this guy looks like a little IJK coordinate system, I'm going to be able to align my fingers in the following way, that using my right-hand rule, I'm going to have things going in the following way. I have T associated with my index finger, going to have N associated with, sorry, it's which one's which? Point, idiot. N goes with the middle finger. And so in my notes, I actually have index finger and pointer finger, which doesn't make any sense. And thumb. So we can think about it this way, that the index finger is going to go in the same thing that our I usually went in. The middle finger is going to be J, and B is going to be K in our usual little thing. Okay, so let's actually do an example here. So I want to find the TNB basis for some vector valued function, vector valued parametric function given by cosine t, sine t, ln cosine t at the point p1, 0, 0. So there's going to be a fair amount of work here because I have to compute lengths of things. Can always save us some work. Okay, so let's figure out how to compute t. If I wanted to find t, I'm going to first need to compute the derivative of r. That's going to give me minus sine t, cosine t, and negative tangent t. How do I get negative tangent? Well, derivative of natural log cosine t is 1 over cosine t, and then I multiply through by the derivative of cosine t, which is negative sine t for my chain rule. Negative sine t over cosine t is negative tangent t. So what I also have to figure out is what time does this point correspond to? So cosine t is going to be 1 when t is 0, sine t is going to be 0 at 0, and natural log of cosine t is going to be 0 at t equals 0. So I really need to also figure out at what point t, what parameter value does this point correspond to? Okay, so r prime of 0, what do I get for that? R prime of 0 is going to give me a negative 0, a 1, and a 0. So r prime of 0 is the vector 0, 1, 0. That is already unit length. So that when I compute t, I know that this is going to be prime of 0 divided by the length of r prime of 0. So I'm going to be taking the vector 0, 1, 0, dividing it by the square root of 0 plus 1 squared plus 0 squared, and I get out 0, 1, 0. So that's the vector t. Now I need to compute n. So n is going to be a little tricky. We don't always need to do this. I could use the second derivative, but that's not an effective method all the time, computationally. So what I'm going to do is back up a step here and compute the length of r prime of t. If I compute the length of r prime of t, I'm going to get the square root of sine squared t plus cosine squared t plus tangent squared t. Sine squared plus cosine squared is 1. And I know 1 plus tangent squared is secant. Going to ignore the absolute value around it. So that if I really wanted to compute the tangent at t, I would be sticking my r prime of t in the numerator, which depends on t, and the length of it in the denominator. So what I mean to say is that here I just found a specific value of the tangent vector. If I want to compute its derivative, I need to find the function that corresponds to the tangent vector for all tangent vectors. So this guy is going to look like negative sine t over secant t, just dividing r prime of t by its length, cosine of t divided by secant t, and negative tangent t divided by secant t. Okay, that guy is what I need to compute the derivative of in order to find n. R prime of t is going to require the quotient rule. I'm going to just speed this up a little bit and notice that sine over cosine is negative sine t cosine t, so that its derivative looks like sine squared t minus cosine squared t. Take the derivative of this guy, which is cosine squared. It's going to look like negative 2 cosine t sine t. And negative tangent t over secant t is the same thing as negative sine t. Its derivative is minus cosine t. So now, when I compute n prime of 0, what I'm looking for is taking t prime of 0 and dividing it by the length of t prime of 0. So t prime of 0, if I plug zeros into the above expression, I'm going to get minus 1, 0, minus 1. And its length is 1 squared plus 0 plus 1. So we get out a vector that is minus 1 over square root 2, 0, minus 1 over square root 2. Okay, b is usually the easiest. We do a lot of work to get t and n, but to find b is pretty easy. B is just the cross product of t and n in that order. If you do it in the wrong order, you'll get the binomial vector pointing in the wrong direction. And you'll be thinking about the left-handed coordinate system rather than the right-handed coordinate system that's following along the curve. So if we compute this, I'm going to get my I, J, K thing out. I know that t at 0, so this is specifically b of 0, can compute it at just one point. It's going to be 0, 1, 0, crossed with minus 1 over root 2, 0, minus 1 over root 2. compute that out pretty quickly. Minus 1 over root 2, 0, 1 over square root 2. So there's my TNB basis. I know that T I can find pretty straightforwardly. Right there. And it requires a little more work always because we have to compute 2 derivatives and 2 normalizations. Okay, something worth pointing out here, and this is maybe a little bit tricky for students to get a grasp of right away, and that is do not use R double prime to find n. It will not quite work. And the reason for that is, well, I'm not going to give you the reason now. I'm just going to tell you, don't do it. Don't do it. We will discuss why it doesn't work at a later time, I think, but I don't want to worry anybody about those kinds of things now. So what I'm encouraging you to do is simply learn the process. If you're really interested in why R double prime doesn't work, the reason why R double prime actually doesn't work is you can figure this out from 13.4, and that is that this guy corresponds to the acceleration, and we know that the acceleration has a normal component and a tangential component. And because the second derivative contains a tangential component, you won't be able to get the proper direction of the normal vector from it. So that's the very short answer about why you should be able to piece this together yourself. But if you want a more in-depth geometric description of it, let me know. I can talk about that with you. Okay, so to wrap things up, T is a unit vector in the direction of motion. So I'm thinking about the motion as far as R of T describing the direction of motion of the head of the position vector given by the function describing the curve. N is a unit vector. So these are always unit vectors that point in the direction that the tangent vectors are pulled towards. And B, the binormal vector, is the second direction vector orthogonal to T. So the idea here is that both T and, if we start with T, we are defining N actually to be a vector that is already orthogonal to T. We know that in 3 dimensions, if I give you one direction, there are going to be 2 directions that are orthogonal to it. Since we already have one of them, it's pretty easy to compute the third one using the cross product to obtain B. Okay, so this is the sort of the main thing. I don't want these guys to look like N's. I really want them to look like hats. So T is orthogonal to the normal plane and the normal plane contains N and B, and B is orthogonal to the osculating plane and T and N lie in the osculating plane. So the whole idea of this perpendicular vector geometry describing planes is what chapter 12 is all about. We see that we came up with these very basic sort of geometric constructions using the cross product and the dot product. And what we're now able to do is talk about different planes that are associated with things moving along a path that we find using simple derivatives, simple rates of change, and this is important. Okay, so I'm going to do one last example here to sort of close this out. So which one did I want to do? I wanted to do section 13.3. I know you guys already did this, but I wanted everyone to sort of see me work through this before the exam that I know you guys are studying for, and see it, you know, because these do require a lot of steps just to see how I'm organizing it. So the question is that we have r of t equal to the natural log of t, 2t, and then t squared. I can't draw a picture of that. I have no idea what that looks like, but we're supposed to give the equation of the normal and osculating planes at the point P0, 2, 1. Okay, so we can do this pretty quickly in the following way. I know I'm going to need derivatives. So first, I'm going to compute r prime of t. That's going to be 1 over t, 2t. And I'm also going to be able to compute the length of r prime of t here. So this is going to give me something of the form square root of 1 over t squared plus 4 plus 4t squared. This might be a useful trick for the exam. Notice that I can write that middle term here, 4t. I can write this in the following way. I can write this as 2 times 2t squared times t to the negative 1 squared. So it looks like 2 times the inner term. We'll be able to factor this guy into 1 over t plus 2t, quantity squared, so that its square root is 1 over t plus 2t. This is indeed a factorable radical. And I can also write this as 1 over t, 1 plus 2t squared if I wanted to. I'm not sure why that might be helpful right away, other than being able to move a factor of t to the numerator and not have a complex fraction. Okay, so now I want to also note that r of 1 gives me 0 to 1. So the point P0 to 1 corresponds to the position of a point along the particle at t equals 1. Okay, so I just wanted to note that right away so that I don't need to reference the function r anymore. I can now compute the function t of t, my tangent vector, by taking my vector 1 over t, 2 to t, my r prime, dividing it by the length of r prime, which is 1 over t, 1 plus 2t squared. So now we see why I brought that 1 over t out. It's going to be easy for me to write this guy component-wise as 1 over 1 plus 2t, 2t over 1 plus 2t, 2t squared over 1 plus 2t. Square. Oh, sorry, I missed squares here. Okay, so the reason, again, why we needed to compute t of t was to compute its derivative. Okay, so we'll kind of not worry about that, right? Yeah, I guess we should. If I compute the derivative of this, should also have a hat on it. Not a hat. It is the derivative of t. Yeah, never mind. The book gets away from this issue that there would actually be a difference between the hat going over. This would be the unit vector associated with t. So the order in which the prime and the hat occur is important for defining what these objects are using the hat notation. But ignoring that, I'm going to now take the quotient rule derivative of this thing, term by term, to find t prime, and simple calc 1 minus 4t over 1 plus 2t squared squared. 2 minus 4t squared over 1 plus 2t squared squared, and 4t over 1 plus 2t squared squared. Which is simply just the quotient rule applied to this step. Okay, so we have basically everything we need at this point. I am going to compute t of 0. Sorry, t of 1. T of 1 I'm going to find by just plugging 1 into everything. I'm going to find that that corresponds to minus 4 ninths, minus 2 ninths, and 4 ninths. Simplifies down to 2 ninths, minus 2, minus 1, 2. Okay, I also can figure out that the length of t of 1, whoops, that's not t. I did the wrong thing here, sorry. Back up a step. Okay, I'm going to start plugging stuff in. I want t of 1. T of 1 I'm going to get by evaluating this thing. At 1. This is going to get me 1/3, 2/3, 2/3. I know that guy is automatically going to have length 1. Right? The denominator is going to be 9. The numerator of the Pythagorean theorem is going to be a 1 squared plus 2 squared plus 2 squared. That adds up to 9. It's going to be length 1. If I take the derivative and I evaluate the derivative at 1, I'm going to get that thing that I had written down before. Negative 2 ninths, negative 2 minus 1, 2, just by plugging stuff in. And I'm also going to want the length of t prime. Here, that's going to be 2 ninths times the length of this vector. 4 plus 1 plus 4. Uh-oh, crashed it. Which is going to be 2/3. But I'm going to get a square root 9 that comes out of this, which is a 3. 3 is going to cancel with one of the factors of 3 and the 9 in the denominator. So that I know t. I'm also going to be able to combine these two together to get n. N of 1 is t prime of 1 divided by the length of t prime of 1. So I'm going to get 2 ninths minus 2 minus 1, 2 divided by 2/3. Gives me the vector minus 2/3 minus 1/3 minus, no, positive 2/3. So I have t and n. B should be straightforward to compute. If I do that, I'll get the vector 2/3 minus 2/3, 1/3. Okay, so for the normal plane, I can compute simply, I know that the normal vector here is going to be my tangent vector. So remember that I define a plane by looking at the dot product of n of x minus some point position vector equal to 0. In this case, that's going to look like the following. My normal vector here is t prime of 1, so it's going to be 1/3, 2/3, 2/3, dotted with x minus, what was the point, 0, 2, 1, equal to 0. And this is my equation for the normal plane. If I wanted to put it in another form, I would simply compute this dot product. But I think writing a plane with the normal vector and the point written this way is the most effective way. It's generally equivalent to the point slope formula in some sense. And then the osculating plane has a normal vector given by the unit binormal, or the binormal direction. Doesn't actually need to be the unit binormal, just has to go in the same direction. So we know I'm going to have n dotted with x minus p in exactly the same way, except this is going to be a very different equation. It's going to look like my binormal vector, 2/3 minus 2/3, 1/3, dotted with the same point, x minus 0, y minus 2, z minus 1, equal to 0. And we're done. Okay, so keeping this stuff organized is important. You need to compute the derivative, the length of the derivative, without plugging things in. You also need to compute t involving the variable lowercase t, involving time. Okay, so I'm just going to get confused saying that and tripping over my words. So I think if you go through and just make stars by the kinds of necessary things that you need to compute, you need to compute r of t, you need to compute the derivative, you need to compute the length of the derivative involving the variable t. You also need to compute t of t so that you can compute its derivative. But that's all you need to do. Computing the length of t prime you can do once you plug numbers in. Okay, so my voice is starting to get a little horsey here, so I'm going to stop here and put this up. Okay, so I hope you guys are studying for the exam. Please let me know if you have any questions, problems, anything like that I can help out with immediately. Be chatty with me, please. If you're lost or struggling, I need to know that. I can help you a lot by having sort of individual chat time with you. So, okay, thank you.